G'day. Thanks for listening. Good morning and good evening to you. This is an agricultural show focusing on plant science, soil science, and microbiology. And the information provided is for scientific and educational purposes, and it's fact-checked. And any of the papers or websites that are being discussed will be put in the description below. And today's topic might be the week 4 of that soil science and technology and soil science and fertilizers course, university course that I took, or it could be some questions. So I'll see how it goes at chat. It's up to chat though. That's what's going to decide what this stream's being called. So if you're watching back, maybe want to fast forward a little bit, use this little slide bar down the bottom and skim through to see when there's some slides, and that's generally when it's going to start. So at least it'll be about the the secondary nutrients, I think we're up to. So yeah, I think it is calcium, silicon. Yeah, it is secondary nutrients. Or it could be a question. So I'll give it another 30 seconds, wait till 2 minutes, and see how it goes. And judge on the last few weeks, there hasn't been a great deal of live spectators at the start. Spectators. I've been watching the cricket. Woohoo, go to the cricket. So anyway, 10 more seconds to go. Alrighty. And that's the 2 minutes. So not much is coming through in chat. So I'll just start so we're on to that topic today. Now, here it is. Yes, calcium, magnesium, silicon. So secondary nutrients. So what are the secondary nutrients? Well, they're calcium, magnesium, and sulfur. I said silicon, so that's why it's good to go through slides. Silicon's actually it's not essential, it's a beneficial. No. Yes, that's right. It's a beneficial, and we'll go through those at a later date because they changed around. Remember, in the 1960s, the nickel was introduced, and then actually I won't go through the history of it. Doesn't matter. Secondary nutrients, so they're required by crop in less than primary nutrient amounts. Secondary nutrients control major plant functions like chlorophyll formation and protein synthesis. Proportions of the Earth's crust is actually made up with these secondary nutrients, and it's 3.2% of calcium, 2.5% of magnesium, and 0.1% of sulfur. And that's why the lime was calcium, they mine it from the earth, and dolomite, which is a combination of the both of them, they mine it from the earth too. Lime, which contains calcium, is applied to raise the pH. Sulfur is used to lower the pH. Remember, sulfur reacts with the water and causes sulfuric acid. Irrigation water may contain on the average 25 parts per million of SO4, 50 ppm of calcium, and 5 ppm of magnesium. Secondary nutrients are called synthesizers because of their function in living organisms. Calcium plays an important role in producing plant tissue, in holding cell walls together, in root system development, and calcium is the 5th most abundant element in the Earth's crust. And it's also involved in the form of calcium pectate, which forms the mill lamina. Roles of calcium. Well, they're good for disease-resistant enzymes, cell walls. That's what that says. Sources of calcium. So you get it from calcite, apatite, dolomite, gypsum. That's one of my questions is sheetrock. Can you just, what happens if you put sheetrock or gypsum that's made in walls? That's because it's got a high percent of calcium in it. That's what mostly it's made of. So it might be good to recycle that. Get onto a plastering company. Yeah, I'll take all your scrap sheets. Just, yeah, sources of calcium. Major sources are weathered from rocks and minerals. And primary calcium-bearing minerals depend on the formation of the proton, the H+ ion in the soil, because that means it's pH dependent. So forms of calcium in the soil. So the mineral particles or calcium carbonate. Do you want me to read them? I should see if anyone's in chat. I don't know how much detail you want me to go into. G'day, Sunshine. Hey, Sunshine RB. How are you? Do you want me to go into much detail? So, can you answer me that? Because I don't know if I want to explain heaps and heaps. You're welcome, Scarecrow. Scarecrow 420, do you want me to go into detail as well? Because I can just skim over the secondary nutrients, or I can explain it quite well and read the slides. So it's about a 30-second delay from the live to when people type. So I've got to give it about another 10 odd seconds. And then I'll get back to it, into the secondary nutrients. Okay. All right, well, I'll skim through them. Proceed as I was. Sure. Oh, all right, well, forms of calcium. Calcium is most present in primary minerals, such as the ones I've already been through, and calcium carbonate is very common. The nodular form of calcium carbonate and amorphous calcium carbonate exist. Okay, that didn't really, I should have skimmed through that. That's what they look like. If you want to go mining and digging, forms of calcium in the soil. There's simple salts that might be present: calcium chloride, sulfate, nitrate, and calcium bicarbonate. And exchangeable calcium, which is one of the best ones, of all of the cations, the exchangeable complex of the soils, CO2 plus is the most dominant cation. Calcium cycle, how does it cycle? So it can be absorbed and desorbed through these particles. It can be weathered in clay to be broken down. From the plant tissue, release it. Plants uptake it. Rain or water dissolves it and dissolves it. Okay, next, that's calcium deficiency, deformation and dying of the tips and meristems, typically death of root tips. So you see it in the new growth, because calcium's a non-mobile element, like boron and manganese. So you'll only see it in the young leaves and the new growth. And curling is another fantastic characteristic, light greening and curling. Also stunted growth, black spots in the leaves. In mild deficiencies, a light green band appears along the margin of the leaves of the terminal buds. Calcium deficiency, blossom end rot. See these tomatoes. Calcium deficiency, tip burn. Isn't that interesting? Some people think that's from feeding. I mean, it is also from salinity, feeding too much too. But yeah, see how it goes more than just the leaf margins. Those leaf tips are the margins. See how it goes actually into the tissue a bit though, so you can tell the difference. This photo's pale leaves or stunted and twisted growth. That's pretty, yeah, it should be a bit lighter than that, but you'll still see the nitrogen has been reduced in the new growth. It's a sign of it. In these apples, black heart and celery is from calcium deficiency. Tipburn in lettuce is, believe it or not, from calcium deficiency. It's amazing how you'd think, wow, what's going on here? It's got to be some fungal disease or something. Just simple calcium. Raise the pH. So cause of calcium deficiency, root zone pH is too high or too low. It's out of the optimum range, 6.5 to 7.5. Or it can be nutrient imbalance in the growing medium. When plants lack a particular nutrient, they cannot create new cells, DNA, or other vital components when calcium is deficient. Another nutrient imbalance in the growing medium is excess nutrients can make plants ill from salinity. Over and underwatering, this is a common reason for unhealthy wilting and dying plants. When calcium is absorbed, it becomes immovable and affects younger leaves. Control measures. How can you fix this stuff? Water helps to prevent calcium deficiency injury, as when growing vegetables outdoors. Calcium deficiency avoided by using the recommended level of salinity for each crop. Like you don't want to go over 2,500, probably 2,500 ppm odd, like an EC3. 750, 21, yeah, something like that. It can cause salinity. Salts is too high and it can't breathe. Another control measure for calcium is to maintain optimum soil moisture levels. Calcium spray helps to prevent calcium deficiency disorders in plants. So you can mix up a foliar spray, maybe 100 ppm. Mulches, and you can source that from lime, would be a good source, organic source. Mulches can be used to prevent plants against calcium deficiency. Addition of lime, you should always use mulches anyway. Addition of limestone helps to boost vegetable crop by increasing alkalinity. Calcium availability factors, the soil pH, cation exchange capacity, and the presence of competing ions. We know about the first two. So the presence of competing ions. Calcium competes with other positively charged cations, such as sodium, potassium, and magnesium. Remember the binding, I'm going to have to show you now. Bonding rate of the cations, where it's that comes into effect then, without going into that. Stick to what I'm talking about, calcium. The presence of competing ions. Applying too much of these positively charged ions decreases calcium uptake by plants. Sodium ions can replace the absorbed calcium, damage soil structure, and decreases calcium availability. It's the bonding strength. It's another cation, so it's competing. Calcium fertilizers. No, I'm not going to talk about these mineral-based ones where you just go to the shop and just buy them. I'm into organics, so I'll be promoting the organic type. That's why I've already talked about foliar spray and the amount. Top dressing is one thing for organics, how you do it. And benefits. Okay. Here we go. Calcium carbonate. That's limestone. So limestone is commonly a sedimentary rock found in widespread geologic deposits. And it usually makes up typically 95% of the limestone if you're going to buy it as lime, agricultural lime. Limestone raises the pH level to a neutral range beneficial to plants. Limestone raises the effectiveness of herbicides. Limestone prevents toxicities in soil and aiding beneficial soil bacteria and microbes, which is massively important as they improve the soil health. And if you've got interested in outdoor growing, you should look at a 1 ton bulker bag for the limestone, because you can get it for, the more you buy, the cheaper it is. For instance, major retailer in Australia here that everyone uses, they've got I think it's a 20 kilo bag for like $30, or at the agricultural wholesalers, it's $9 for the same size bag, or if you go and get a 1 ton, it's $250. These are Australian money. So it's always good to have, because when the plants grow, they release their protons, which is going to makes the soil go more acidic. So you're pretty much always going to need a bit of a top up, unless you can get things cycling extremely well. But if you want to grow and take things out of the soil, that's when you're going to have to add back in at a probably decent rate, and that's when this will come in handy. Sulfur! So more than 95% of the total sulfur in the soil is present in the organic matter. The oxidation of sulfur is mediated through thiobacillus bacteria. The soil rich in organic matter will have high amounts of sulfur. That's where organics is to go. In most cultivated land, sulfur ranges between 30 and 50 milligrams per kilo. Coarse textured sandy soil has low sulfur content than fine textured soil. Sulfur content more in subsurface soils is more, sulfur content is more in surface soils than subsurface, and bulk of inorganic sulfur in rocks is present as pyrites, FeS2. The role, I should just see if there's any questions or anything. No, still humming along. Sulfur, roles of sulfur. What is sulfur's role in plants? Well, it's essential for amino acids, photosynthesis, symbiotic nitrogen fixation for legumes, because you want to grow them in your non-cropping period. Sulfur also activates enzymes and coenzymes, and is essential in the synthesis of proteins, including building up seed reservoirs. So the characteristics of sulfur: it's the 13th most abundant element on the Earth's crust. Concentration of sulfur in plants range from 0.1 to 0.5%. So it's not much, but it is needed. It's essential for their growth and development. Another characteristic of sulfur is ionic forms. SO4-2. It's abundant. Okay, very good. Sulfur cycle. How does it cycle? Well, there's a little bit to atmospheric sulfur, because it comes in the form of sulfuric gas. And once that gas is broken down, it forms as residue. Also forms as sulfate. Once it's oxidized by bacteria in the soil, then it's reduced to H2S. And then there's all sorts of oxidation happening. Plants can uptake it, manures and biosolids. Good sources, and rocks and lithotrophic bacteria. The steps in the sulfur cycle are formation of inorganic sulfur, then it oxidizes to sulfate, then it assimilates reduction to sulfate sulfide, then incorporation of sulfide into organic compounds. Remember, the 8s and the ides are the negatives, so that's all a negative anion. Transformation of organic sulfur. So these are the steps that it goes through in its sulfur cycle. It transforms, gets oxidized. We go through them. Importance of the sulfur cycle. This is probably a bit better. Importance in agriculture in the sulfur cycle. Contributes to the majority of metal deposits because it can act as an oxidizing as well as a reducing agent. It serves as a source of energy to the sulfur-reducing bacteria present. Reduces global warming caused by greenhouse gas by absorbing the UV in the sun. And it helps plants. Mineralization. The oxidation of organic matter into sulfur is done by microbes and is called mineralization. Because it's immobilized when it's in the organic matter, and when it's taken out, it's mineralized into its mineral form. Mineralized process is expressed as that the formation of the end product of sulfur is associated with the formation of H plus protons, hence this process lowers the soil pH. The rate of mineralization is affected by these factors. So it can be mineralized out of organic matter by moisture, air, temperature, and the pH are all contributing factors for it to be mineralized. Immobilized is the one. That's the go, because that's the organics. So it's bound up into something, into organic matter, and you want to break it out of that. So immobilization is only a temporary phase because the microbes are going to break it down and mineralize the components. Sulfur in the soil is associated with organic carbon in a fixed carbon to sulfur ratio of 140:1. Immobilization of sulfur takes place in soil when the ratio is either carbon or nitrogen to sulfur is very wide. The optimum temperature for immobilization is 35 to 40 C, or that's 90 to 100 F. Sulfur oxidation reduction. So this is how thiobacillus reduces it. So sulfate can be reduced to hydrogen sulfide by desulfurfibrio or desulfursulfate omaculum. A couple of bacteria go through and reduce it and then oxidize it. So by having these correct microbes, so if you've got, for instance, a sulfur hungry plant, cultivar, vegetable, fruit, whatever it might be, you can go and source these microbes and put organic matter in, and through these microbes will increase the amount of sulfur available to your plant. That's one instance in how to make bio-fertilizer or microbes work for you, which is what I'm fully into, because it's the future. It's how the earth worked. Okay, what's other forms of sulfur? So there's inorganic and there's organic. Some inorganic forms are the ready soluble sulfates, absorbed sulfates in soluble sulfates, and there's co-precipitated with calcium carbonate, reduced inorganic sulfur compounds such as sulfide and elemental sulfur. And the organic forms is hydroiodic acid, reducible sulfur, carbon bonded, and residual or unidentified sulfur. Okay. Didn't really enlighten. Forms of sulfur, readily soluble. So the readily soluble ones are the mineralized ones that are already available. However, the coarse textured soils like sandy and sandy loam soils contain sulfur less than 5 milligrams per kilo. But in sulfur deficient soils, easily soluble sulfate contains between 5 and 10 milligrams per kilo. Righto. Absorbed sulfate, so contains higher amounts of iron and aluminium, which isn't good. They're top of the cation. They're both cations, and they bond the strongest. So if there's, for instance, I'll just continue. Contribute sulfur requirement in highly weathered soils. So the absorbed sulfates contribution is found higher at depth ranges from 15 to 75 centimeters below the surface. Absorbed sulfate can account for up to 1/3 of the total in subsoils and is less than 10% of the total sulfur in the surface soil. So co-precipitated forms with calcium carbonate is another form. Sulfide form, elemental form. I'm into the organic form, which is immobilized forms of sulfur, highly reducible sulfur, carbon bonded sulfur, which of the carbon bonded sulfur, the fraction of sulfur amounting is about 20% of the total organic sulfur. Residual or unidentified sulfur, this accounts to 30 to 40% of the organic sulfur, and it's the most stable form of sulfur. Then where do you get your sources from? Sulfur occurs as sulfide in igneous and sedimentary rocks. As a fertilizer, you can buy it. And sulfur-bearing minerals in rocks are gypsum, epsomite, mirabilite, pyrite, chalcopyrite, cobaltite, and galena. So that's the organic sources you can get it. But by getting it from agricultural lime, it should be mined from the earth. So it's a source that is good for calcium, not for sulfur, sorry. About 95% of sulfur in the soil is contained in organic matter, immobilized. Sulfur dioxide in the atmosphere is the highest in industrialized areas. So isn't that amazing? You can pull it out of the atmosphere, so that's where you find the highest, the lower pH soils as well for that reason. Sulfur is present in irrigation water as sulfate sulfur. Cow and pig manure, compost and poultry manure, it also exists. And acidic rain provides sulfur, which isn't good, but it still provides it. There's some different, if you were to buy it in a mineralized form, that's the amount of sulfur percent that it contains. Sulfuric bentonite. Oh wow, use bentonite to seal up ponds. Ammonium sulfate. All right, I'm not going to go through really any of these because that's the form that you buy it, except for this one. Gypsum, calcium sulfate. Gypsum byproduct comes from fossil fuel power stations where sulfur is scrubbed from exhaust gas. It is also called land plaster. So that was the thing I was wondering before. Can you just use your gypsum? But it comes from, look where it's made from that. So you might be able to recycle it, but yeah, it's still not 100% organic. Factors affecting sulfur availability, the type and amount of clay. So the higher amount of clay decreases sulfur availability, as well as the pH. The pH of released sulfur is directly proportional to the soil pH up to 7.5. In organic matter, soil containing high organic matter have higher amounts of sulfur. So organic matter is always the go. You can't go wrong. Because remember, it only needs, 0.1 to 0.5% sulfur in the plant tissue. So it's not much. So by having that in your organic matter, you've won the battle. You don't have to worry about buying it in all sorts. Just have the right microbes to break down your well-sourced organic matter. And the factors affecting the sulfur availability is the salt content, cations and anions, and presence and absence of vegetation. Alternate water, and also alternate watering and wetting and drying, and interaction of sulfur with other nutrients is not good. The application of zinc increases the utilization of sulfur. The interaction between nitrogen with sulfur found to be synergistic, and a positive interaction has been found between sulfur and phosphorus. Factors affecting the sulfur availability. This is pretty cool. On the y-axis, the availability of elements, and on the x-axis, the pH. So calcium and magnesium, as the pH goes higher, the factors affecting sulfur availability are higher. The availability elements are higher, which affect the sulfur. Put it another way. Nitrogen to sulfur ratio, you want to get the right ratio. Because for instance, cereals, you want 11 or 12 is to 1 of nitrogen to sulfur. For legumes, you want 15 to 16 is to 1. And a normal fertilizer that you get is a ratio of 10 is to 1. In the absence of S or sulfur in the soil, utilization of nitrate can be hampered. So all the different reasons why things mix together. Now, deficiencies is a bit harder to pick, and it should first appear in the younger leaves. Fruits do not fully mature and remain light green, so it's a pretty good indication. Leaves become pale yellow, poor nodulation in legumes. There you go. You can see on the left is the control, on the right is the sulfur deficiency. This is in wheat. Just like a yellow, you think, oh, geez, it's probably a nitrogen thing. But notice it's in the younger leaves, not the older leaves. Some cabbage, banana, groundnut, yum. Boiled peanuts, yum. Lettuce, potato. Salt deficiency versus nitrogen deficiency. We'll kind of cover that. Just the older leaves, the younger leaves. You can read that later if you want. Magnesium is an essential constituent of chlorophyll in the plants. It actually has the chlorophyll pigment has one nitrogen atom in the middle and has 4 magnesiums around it. Magnesium is absorbed by plants from the soil as Mg2+. It is about 2% of the Earth's crust, ranging from 0.1 in coarse sandy soils of humid regions to 4% of fine textured soils in arid, semi-arid regions. Magnesium plays a major role in photosynthesis. Magnesium also helps to activate some specific enzyme systems. The heart of each molecule of chlorophyll is an atom of magnesium. Righto. Well, what was I just talking about? Oh, I was wrong. Because look, it's the other way around. It's magnesium, and then 4 atoms around the outside of it are nitrogen. So I had it back to front. Sorry. Lucky for slides. Magnesium functions includes phloem loading and sucrose transport in sink tissues, improves shoot to root ratio, helps with root growth, helps enzymes, chlorophyll pigments, and photosynthetic related processes. The cycle, as it gets through, it can be leached down. Organic matter is a great source of inputs and outputs for it. Mineral or organic fertilizer, harvested crops, residue, organic matter can erode out. Primarine is broken down with microbes and different mineral types. Okay, good. Source of magnesium, dolomite, lime, Epsom salts, ceriosite, potassium, magnesium sulfate. And you look on the right here, percent of magnesium in these, if you want to get it. So dolomite, dolomitic lime, 8 to 20%. That's, well, the dolomite that I've been looking at, I think it's about 30 to 35%. Because calcium 60 to 65. I think it's something like that. So you can get different, the manufacturer can make up different percentages for you. And believe it or not, look at Epsom salts. People always think Epsom salt's a good source of magnesium. It is, but it's only 10% of it. So what's the other 90%? So you got to remember that. Forms of magnesium. Well, there's forms in soil solution, exchangeable magnesium and non-exchangeable magnesium. Gets a bit technical. Octahedral clays. Forms of magnesium. This is the clay sites. You want it to be exchanged in the different types of clay, but you've got to have the right type of clay to do that. Forms of magnesium, plant magnesium uptake, magnesium in the soil, magnesium in structural form. Root exudates and soil microorganisms affect magnesium release. See that? Soil microbes affect magnesium release. Magnesium uptake. Plants take magnesium in its ionic form. It can be magnesium uptake is dominated by 2 processes, passive and diffusion. Passive uptake is driven by transpiration stream, and diffusion, magnesium ion moves from zone to high concentration to the lower concentration. Magnesium deficiency. The loss of the healthy green color is the first indication. Similar to nitrogen, magnesium is highly mobile in the plant, and deficiency symptoms first appear in the lower, fatter leaves, bigger, older leaves, not the newer leaves. Magnesium deficient plant has less than 0.1% of magnesium. Deficiency common in plants grown on coarse textured acidic soils. You first see interveinal chlorosis, so you'll see the yellowing of the veins within the leaves, yellowish of tissue also along the leaf margins and between the veins, rendering the older and middle leaves. Magnesium deficiency, the proportion of protein nitrogen decreases and that of non-protein nitrogen increases. So you can see there, see how all the veins are still left yellow? So it's just all the tissues in between it. Another example. I don't know if this is purple's to do with phosphorus. I'm not sure about this one, but I agree with this one. This is a pretty good one. In the early stages, you'll see on the edge of the leaf margins. Middle stages, it's thicker, and late stages, it kind of looks like even you'd call that potassium. But potassium, it would have, all of these would be dead on the outside of it. Actually, that might even be potassium, because if it's a later stage, there should be more yellowing in that. So see how it's very similar symptoms, but by looking at the leaves and knowing them, you'll see the early stages and you'll see it starting to develop. Magnesium deficiency. Well, here's the physiological impacts of the deficiency in plants. How it starts to reduce chlorophyll biosynthesis, and then oxidative enzymes form, which isn't good, and impaired phloem loading, which isn't good. It just keeps cascading down when it's deficient. Magnesium loses from soil. Magnesium losses from the soil are removed in harvested crops. Leaching losses of magnesium slow, show high variability depending on the nature of the soil, the amount of percolating or rainfall, irrigation, the kind of and quantity used, and the level of exchangeable magnesium. Another magnesium loss from the soil is erosion of the topsoil and fixation into unavailable forms. Factors affecting magnesium availability are low temperature, dry soil, high level of competing elements, effective soil pH. So in low pH soil, the solubility of magnesium decreases. Manganese and aluminium become more soluble and reduced magnesium uptake. Acidic soil increases the tendency of magnesium to leach because they have lower cation exchange and can't bind to anything. Factors affecting magnesium availability: excessive application of potassium and ammonium, addition through fertilizer, manures, and rains. Because farmyard manure and oil cakes are a rich source of magnesium. Basic slag contains 3 to 4% magnesium, and serpentines contain 26% magnesium. There you go for your organic heads. Here's a case study. This is to do with this is to do with the elements in India, where this course is written. And it's nutrient antagonism. Oh, wow. I'll put this up. So if you want to read about how they, like for instance, what we're talking about, all right, calcium. High levels of calcium can accentuate boron deficiency, Liming can decrease the uptake of boron, copper, iron, manganese, and zinc by raising the soil pH. So where's it today? No, it's at 1. Magnesium. Manganese, no. Should be on. So it's just how the nutrients interact with each other. It's pretty cool. It's what's that soil antagonism chart? Mulder's antagonism. Mulder. Let's have a look at that. Should see if there's any questions. Oh, geez, there's a fair few. I'll stop sharing for a bit then and scroll up and look at the questions. So this one. What? Oh, I'm not in that. I was in the wrong page, sorry. Sure. Sunshine RB says, how effective is nitrogen fixation from alfalfa and clover, etc.? I heard it's minimal. Well, hello, Stony Creek. There you go. Yes, it can be minimal if you don't have rhizobium. But if you have the root nodule forming nitrogen fixation bacteria for legumes, which is rhizobium, it's no worries. So you got to get, when you buy your legumes, you get you can get inoculated stuff, which is blue, which is inoculated with rhizobium. So what I do is, it's quite a lot of more expensive. So I'll mix usually get red clover. It fixes a bit more than white clover. But I got both. So I'll mix them and a few other legumes, sun hemp and buckwheat, and a few other legumes together with those blue inoculated clover, and therefore the rhizobium will get around on the other seeds. So I'll mix it around for a while, and it should touch the other seeds. And then when I'll broadcast it out in the area that I want, it'll all be mixed in. So rhizobium will be quite dominated in the area where those legume seeds are starting to germinate. So I hope that helps with that question. So yes, it can be minimal if you don't do it properly, if you don't have the root nodule forming nitrogen fixation microbe. Stony Creek says, good one. CC, thanks, mate. Sulfur is underrated, especially in different cultivars. Yes, for sure, mate. It's it's fantastic for flowers. G'day. I'll get strawberry potted here. It's got sulfur added for extra flavour in the fruit. Sulfuric compounds in the strawberry plants, I'm guessing. Yeah, or probably your organic manure that you're using, because I think you're into organics. So it would be in your organics, bound up in your organic matter somehow. And you've got the right microbes to break that down, making the sulfur available to your plants. Sunshine RB says, use sulfur to lower pH, works great. Oh yeah, mix that with a bit of water, you got your sulfuric acid. Well said, mate. I'll just pull up that chart here. The Mulder's, I'm going to share it. Okay. Oh, back to share screen, sorry. So we're pretty much at the end, so drop your questions if you have any. Here's the chart that sort of backs up what those nutrient antagonism of these two were. So if you want an easy chart, like maybe to put on your wall, after you've read all this a few times, because it's really hard for it to sink in, because this interacts with that. A lower amount of that equals that, and that's exactly what this shows. So antagonism. So it's decreased availability to the plant of a nutrient due to the action of the other nutrient. So where's it one way? So zinc affects iron. So it's potassium is synergistic actually with iron, so it doesn't affect anything. So it's, yeah, just to be technical, because that's what this course is all about. All right, let's see what the last few slides are. Antagonism related to magnesium. Potassium has an antagonistic effect, inhibiting effect on the absorption of magnesium. So there's another antagonism effect. So by a balanced ratio, it absorbs the best. But by having a high amount of potassium, you only can get a low amount of magnesium. So you can't just go and throw, so you've heard people say lower the better amount of elements, and that's why organic matter is brilliant, because only the right bits get broken down at the right stages where they're wanted. It's otherwise you're left with all this if you're into mineral fertilizer. Oh, here's that chart that I was just looking for. It's called Mulder's chart. They didn't give him props. This has got a light one too. Light antagonism. So it's so technical. Agronomic effect of magnesium. What's this x-axis? Agronomic efficiency of magnesium fertilizers. Okay. So that's how, because that'd be mineral fertilizers, not organic. Relationship between secondary nutrients in the crops, with magnesium nutrients and pH in the soil. Oh, here's a good little summary of them all, I suppose. You can see having a low pH of 4.5, you're not going to really get any. At the most, you can get 50% of those potassium, calcium, magnesiums that's in the soil. So by raising it just a little tiny bit, so you have a little bit of lime, and all of a sudden it makes it pretty much fully available. You go up to the 6.5, which is optimum, 6.5 to 7.5. The reason why they say that is because, look, pretty much all the elements, the 17 essential elements, are available in good amounts. So your chances of getting a deficiency are low. So that's why whenever anything happens, the first thing you pretty much check is your pH. Good way to end it. Thank you for the 2 people watching, and for you who watched it back. I hope that helped. It was, yeah, it's a good eye-opener just to know some fact form about elements. And that was a whole week of lectures I just went through then. I'll share screen again. And this is what we went through then, all those, which is a week of lectures. And what's the other micronutrients? So if nothing happens next, this is what I'll be putting for today's title. If we don't get any real questions to derive a stream next week, or especially at the start of the stream, because that's when I got started, I'll be starting with this one, micronutrients. And then I've done that, which I've already done that. Then it'll go into the fun bits and the brilliant bits, the organics. That'll be a long stream. These few, bio-fertilizer, biochar, holy mackerel. They'll be really long streams because I just love the microbes. You get the right microbes, they can work for you. That's it. It's brilliant, like blimmin' brilliant. There's way more than 1 or 5 different nitrogen-fixing microbes. I'm using 5 myself. It's just excellent. They blimmin' work really, really well. There he is, Aussie Jeffro. G'day, Aussie Jeffro. There you go, mate. He says, yes, definitely very informative as usual. Thank you so much. Have a good Christmas, my friend. Oh, thanks for the nice words, mate. I hope you and your family do too. Very nice. Oh, I'm still sharing. I'm not sharing now. Oh, I'm showing what we're going to do next week, which will be right in the holiday period. I hope everybody has excellent holidays and enjoys the cricket like I am. It's so good. Yeah, that's what I was up to. I got sidetracked on microbes again. But soon, that will be probably next year. Oh, well. Yeah, because this one's next week. Some mini slides. Oh, yeah, there's quite a few. Probably about the same as today. What's the first one? Let's have a sneak peek. That's right, just flashes. Soil health indicators. This is brilliant. So this is really your substrate indicator. So it's the macronutrients, micronutrients, physical conditions, biological, and stress conditions. So to make up your substrate is three things. It's the chemical, biological, and physical properties. So if you have all them in check, things flow well. Yes. Well, I reckon that's it for today. I hope I can see you all next week and we can go through a bit more. If you have any questions, please ask them at the start of the stream and we can make a stream out of your questions if you have a few or a large topic, or I can answer them through the stream like I have today. But it was very good. I enjoyed it. Thank you all for listening. And I hope you enjoy your plant science, soil science, and microbiology as well, like I do. It's really good. Good fun. Thanks again. You're welcome, mate. Thanks, Aussie Jeffro. Yes, I enjoy it. It's even next semester at university, I've got 2 microbe courses, new ones, and 1 plant breeding course. And I just can't wait. The more I learn about the microbes, the more I just go, wow, why aren't we using them for our benefit in every aspect? And it's because, like, they've even got ones that break down plastic. There's a few different types. Actually, I'm not going to get talking about microbes. Ask me some microbe questions at the start of the stream, and we're going to have a microbe special again. I love it. There. I'm not going to talk about it. Anyway, hope you enjoy your cricket. And happy holidays, too, to everybody, where everybody's starting to get time off work, and hope you enjoy yourself. I really hope you do. And smile. And contact the people who don't have many friends or like relatives, who are bad relatives, because they'll be lonely and it's just good to share some good energy around. There you go. Nice ending words for today. So happy breeding, happy growing, and good health to you all. Hope to see you next week. Bye-bye. Thank you very much for listening.